already know that a linear transformation mapping a vector space into itself depends upon the basis B. Now we're going to define 4 matrices that we will be using. A is going to denote the standard matrix of T relative to B. A prime will denote the matrix of T relative to B prime. Now that's basis B prime. P is going to be the transition matrix from B prime to B. P inverse is going to be the transition matrix from B to B prime. Now this is the same transition matrix that we talked about before when we were in change of basis for coordinates. So it's the same one, same concept. And we are going to get P and P inverse the same as we did before. I have a little chart to show you how the matrices are related. V with respect to B is going to equal to P times V respect to B prime as we go up. Now the image of V under T respect to B is going to be A times V respect to B. The image of V with respect to T, the image of V under the transformation T respect to B prime is going to be P prime times T of V respect to B. And we see that T of V respect to B prime is A prime times V respect to B prime. So you can see how the chart goes. Now we're just going to read the chart to get an important relationship. We can go the direct route, which is what I said, A prime times V respect to B prime is equal to the transformation of V respect to B prime. That's just going straight across. Now we can also start with V prime of B, and we can multiply it by P, and that gets us up to here. We can multiply by A to get to here. We can multiply by P inverse to get down to this position. So we can go around to get to the same place. So we start with V respect to B prime, multiply by P, that gets me to V respect to B, multiply by A, that gets me to TV respect to B, multiply by P inverse, that gets me to TV respect to B prime. Now equating these two, I can see that these expressions must be the same because they're equal to the same thing. Well, if that's the case, then the A prime must equal to P inverse AP. For square matrices A and B of order n, A is similar to B, I'm defining similar, if there exists P such that B is equal to P inverse AP. So from the last statement, we can see that A prime is going to be similar to A. So this is definition. A is similar to B if there exists P such that B is equal to P inverse AP. So A prime is going to always be similar to A. But B is similar to A if I can find an invertible matrix P such that P inverse times A times P is equal to B. Let's look at an example to try to tie some of these things together. T maps the plane onto the plane, or maps 2 space into 2 space. T as a function of xy is equal to x plus y, x minus y. B prime is equal to 0, 1, 1, 0, and B is equal to 1, 0, 0, 1. In other words, B in this case is the standard basis for R squared. Find A, P, P inverse, and A prime. Well, since we're using the standard basis, A is going to be the standard matrix for T. So A, we can simply read off as being 1, 1, 1, negative 1. To find P, we want to transform B prime into IP. Now we've done this before. Well, to transform B prime joined to B into IP, we need to go to B, which is going to be 1, 0, 0, 1, and B prime 0, 1, 1, 0. Well, we already have the I here. So that's already of the form IP. So we can see that P is equal to 0, 1, 1, 0. To find P inverse, transform B prime B into I P inverse. So B prime is going to be 0, 1, 1, 0. B is 1, 0, 0, 1. And I want to transform this into I and P inverse. Well, to transform this into I, all I need to do is interchange the rows. So interchange the rows to get 1, 0, 0, 1, 0, 1, 1, 0. So here's I, here is P inverse. So we can see that P inverse is 0, 1, 1, 0, which in this example was the same as P. So I said in the example, find A, find P inverse, and now find A prime. Well, we can use what we deduced earlier to get A prime. A prime is P inverse AP. So we know that A prime is P inverse AP, which is going to be 0, 1, 1, 0 times A, which is 1, 1, 1, negative 1, times P, which is 0, 1, 1, 0. This is going to be 0 plus 1, 0 minus 1, 1 plus 0, 1 plus 0, times 0, 1, 1, 0. 0, negative 1, 1, 0, 0, 1, 1, 0. So there is A prime. Now let's look at an example in which neither base is the standard base. Base B is 1, 1, negative 2, 3. B prime is 1, negative 1, 0, 1. And A is 3, 2, 0, 4. Find P, P inverse, and A prime. To find P, what we want to do is to transform B prime into I P. Well, B is going to be 1, 1, negative 2, 3. B prime is 1, negative 1, 0, 1. Well, I can use my row operations, so I need to multiply row 1 by negative 1, add to row 2. One times negative 1 is negative 1, plus 1 is 0. Negative 2 times negative 1 is 2. 2 plus 3 is 5. Negative 1 times 1 is negative 1. Minus 1 is negative 2. Negative 1 times 0 is 0. 0 plus 1 is 1. Multiply row 2 by 1/5. And I get 1, negative 2, 1, 0, 0, 1, negative 2/5, 1/5. Multiply row 2 by 2, add to row 1. Two times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. 2 plus negative 2 is 0. 2 times a negative 2/5 is a negative 4/5. Plus 1 is a positive 1/5. 2 times a negative 2 times, or see, I'm multiplying by 2. 2 times 1/5 is 2/5. Plus 0 is 2/5. So we get that P is equal to 1/5, 2/5, negative 2/5, 1/5. And I also said find P prime. To get, or not P prime, P inverse. To get P inverse, transform B prime B into I P inverse. So B prime, 1, negative 1, 0, 1. B, 1, 1, negative 2, 3. All I need to do here is to add row 1 to row 2. 1 plus negative 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. Negative 2 plus 3 is 1. So here we have I. So that means that P inverse is going to be 1, negative 2, 2, 1. Now, of course, we could also have gotten P inverse by inverting P, but this method is easier. Now we need to find A prime. A prime is equal to P inverse A P, which is equal to, if you look back in your notes, P inverse is 1, 2, negative 2, 1, times A, 3, 0, 2, 4, and I gave you A in the problem, times P. And P, we see is 1/5, negative 2/5, 2/5, 1/5. So A prime is P inverse AP. Three plus 0 is 3. That's going to be 2 minus 8 is -6. 6 plus 0 is 6. 4 plus 4 is 8. Times 1/5, 2/5, -2/5, 1/5. That's going to be 3/5. Minus 3/5 plus 12/5, which would be 15/5, which is 3. It's going to be 6/5 minus 6/5, which is 0. It's going to be 6/5 minus 16/5, which is a -10/5, which is a -2. 12/5 plus 8/5, which is 20/5, which is 4. So we get A prime is equal to 3, 0, -2, 4. Let's continue with the same example. Given that vector B with respect to B prime is 1, -3. Find the coordinates of V with respect to B. Well, notice that the coordinates of V with respect to B is P times the coordinates of V with respect to B prime. So I can use the coordinates of V respect to B is equal to P times the coordinates of V with respect to B prime. We can read that off the chart. Well, if you look back in your notes for P, you'll see that P is 1/5, 2/5, -2/5, 1/5, times the coordinates of V with respect to B prime, which would be 1, -3. One-fifth minus 6/5 is a -5/5, so that would be -1. A -2/5 minus 3/5 is a -5/5. That is -1. So the coordinates of V with respect to B would be -1, -1. Now let's find the coordinates of the image of V with respect to B. Well, we can see that the coordinates of the image of V respect to B would be A times the coordinates of V respect to B. Reading the chart again. So I'll write T V respect to B is equal to A times the coordinates of V respect to B. Well, if you look back at A, you'll see that was 3, 2, 0, 4. We've just calculated the coordinates of V respect to B. So that would be a -1, -1. So then that's going to be a negative 3 minus 2 is negative 5, negative 4. And finally I said, get the image of V, the coordinates of the image of V with respect to B prime. Well, there's two ways of doing that. I can go all the way around, or I can go directly. So I could take this answer, multiply it by the inverse, because we already have this answer, multiply it by the inverse. Or I can go back to V of B prime, multiply it by A prime. I think I'm going this way. If you look back, you'll see that A prime, so what I'm going to do is, the image of t, the coordinates of the image of t with respect to B prime is equal to A prime times the coordinates of V respect to B prime. A prime is 3, 0, negative 2, 4, times the coordinates of V respect to B prime is given to be 1, negative 3. That's going to be 3 plus 0. Negative 2 minus 12 is negative 14. Now let's look at a theorem that gives us some of the properties of similar matrices. So let A, B, and C be square matrices of order n. First property, A is similar to A. Second property, if A is similar to B, then B is similar to A. So this is kind of like the reflexive property. A reflects back upon itself. This is the symmetric property. If A is similar to B, then B is similar to A. And we have the transitive property. If A is similar to B and B is similar to C, then A is similar to C. So reflexive, symmetric, transitive. I'm going to prove the third property for you. And the first two proofs are a little easier than this one, but it involves the same concept. So I'll prove the property 3. So if A is similar to B and B is similar to C, then A is similar to C. Now if A is similar to B, then that means that A is equal to P1 inverse B P1 for some P1. So there is an invertible matrix P1 such that A is equal to P1 inverse B P1. That's the definition for A being similar to B. Now, if B is similar to C, then that means B is equal to P2 inverse C P2 for some matrix P2, because that's the definition of similar. Now, what we want to prove is that A is similar to C. So I'll start working with A, and A is going to be P1 inverse, and I'm going to replace B by what it's equal to, which is P2 inverse C P2 times P1. So all I'm doing here is replacing B from this statement by what B is equal to. Now, by the associative properties, I can write A is P1 inverse, P2 inverse, times C times P2, P1. That's the associative property of matrix multiplication. Now, from the properties of inverses, I know that P1 inverse times P2 inverse is P1 times P2 inverse C P2 P1. Actually, I know this is P2 P1. Changes the order of the inverses. There it goes from 1, 2 to 2, 1. If you go back and look at your property of multiplying inverses, P1 inverse times P2 inverse is P2 times P1 inverse. Well, this proves that C is similar to A, or I should say A is similar to C. Because notice it fits the pattern A is equal to an inverse matrix C times a matrix. So it fits the pattern. In fact, I can just come to show you that. Let matrix P equal to P2, P1. So we would have A is equal to P inverse CP. So if you don't follow it this way, then follow it like that.